Yeah, thank you, Iman. Hello, everybody. Welcome to my study guest room in South Yarra. So today I'm going to talk about assignment and temporal logic planning for threat seduction decoys. So this is work I've been working on with Iman and Chris Manzi, and also two PhD students, Mitchell, who had given a talk in this seminar series a few weeks ago, and Elad. And this work here I'm showing today is in collaboration with DST, in particular the DST group in Adelaide. So the problem we're looking at is seduction of threats. So we're looking at the problem of controlling threat seduction decoys, and in particular we are interested in controlling reusable decoys. So typically single-use hardware is used for threat seduction, and this is very expensive, and so the idea came up to control reusable decoys. And the challenge coming with that is that typically this kind of hardware is much slower, and then the control problem becomes time critical, as the decoy has to reach a certain position within a tight time frame before it is so it can protect the asset. So here in this figure, I'm trying to show you a kind of setup that we're considering. So we're looking at protection of an asset, a surface asset here on the surface with this cross from the ground here in blue, and there's an incoming ballistic threat. And the idea is that we can maneuver a decoy somewhere in the path between the threat and the asset, so that we can distract the threat. In particular, we need to reach the so-called tracking cone. So this this area in front of the threat with a certain opening angle, so this threat is traveling towards the asset. We need to get into this proximity, so in the region where the threat tracks its targets, as shown here in this cyan or blue cone. And we need to reach this cone before the threat gets too close to the asset. So when the threat is too close to the asset, it gets closer than the so-called burn through range. The decoy cannot fulfill its task of emitting a signal that projects a fake target to the threat. So the objective is to move the decoy in this cone, to reach the cone before the threat reaches the breakthrough range, and then emit an electromagnetic signal to portray a fake target. This is called jamming. So interfering with the radar of the threat is a jamming objective, or spoofing, in that we are projecting a false target. Once the decoy is in such a state that it can project a false target to the threat, the decoy then moves away from the asset in the attempt to lure the threat away from the asset. While the decoy is luring the threat away, there's a requirement that it moves in a way that is indistinguishable from the asset, so that from the threat. So from the perspective of the threat, the decoy should move in a way that it looks like the asset is tracking. And in particular, this is manifested in the Doppler shift. So the requirement is that the Doppler shift experienced from the threat radar should be bounded, should not change too much compared to the Doppler shift that it experiences when tracking the the asset. So this is the kind of threat seduction scenario we're looking at. Then in particular, we're looking at when there are multiple threats. So here we have these red dots, multiple incoming threats, and there's a surface asset here in the middle in blue, moving slowly. So the goal is to try to deal with all the threats as reliably as possible. And the overall task involves going to a place where we can start the seduction and then luring away. But the assumption we're going to make here is the quicker we can get into a position where we can start the seduction process, the more likely we are to have success. So our goal is to, in terms of navigating these decoys to start off with, is to control the decoys such that the minimum or the longest time required to be able to start the seduction process of all the decoys is minimized. So the first problem is we have multiple decoys. We say we assume we have more decoys than threats. The first decision to be made is which decoy should deal with which threat. So the first problem is task assignment. The task being position itself, a decoy to position itself to seduce a threat. And so ideally the overall goal is to minimize the longest positioning time. As this happens in parallel, the longest positioning time will be the overall time it takes to deal with all the threats. So that's the main objective of the assignment problem. But we also want to investigate if particular choice of assignment may give us properties that we can use or that can facilitate the path planning in the second step. So the second problem is then the motion control. So how do we control the decoys that we can move them in a certain position? So we need to reach this tracking cone within a certain time. But we also have temporal components. So we need to be in the cone. It's a subtask. Then we also need to make sure that at that time the threat is in a certain position. So it's time critical. So there's timing. So we have an objective that combines several conditions that are combined in logics and also in time. So my talk is going to be split up into these two main components, into task assignment and then the motion control in the second part. Starting off with task assignment. For the initial assigning decoys to threats, we need to have some estimate of how long it's going to take for a decoy to maneuver itself so it can start the seduction. So for this, we select a single point as a target for every threat, and we call this the nominal seduction location. And then the time it will take for a decoy to start seduction, if we assume a constant reference velocity for all the decoys, will be proportional to the distance of the decoy's starting position to this destination where we can seduce, or we think we are confident that we can seduce the threat. So then this can be thought of as the cost of an assignment. So then to minimize the overall time, as all these decoys travel at the same time in parallel, we formulate the so-called bottleneck assignment problem, where the objective is to minimize the maximum of all the assigned costs. So this is an optimization problem over binary variables, here pi, where an agent can either be assigned to a task or not. And in particular, we say that one decoy has to be assigned to every threat. So this is this first constraint. And also at most one threat per decoy. So we assume that there are more decoys than threats. So there may be decoys that are not assigned to any threat, but all threats should have one decoy that's assigned to them. So this problem is a well-studied assignment problem. It can be interpreted here as a integer optimization problem or a graph theoretical problem where we're looking for maximum cardinality matching. Now there's a lot of literature on this, and actually Mitchell a couple of weeks ago talked about how to solve this problem in a distributed way. Here today, I'm just really looking at the application of this to the navigation of decoys and investigating properties that we obtain from solving this assignment problem. So to start off with, to be able to get the weights for the assignment problem or the weights in the graph, we need to determine one position that we want to navigate towards that determines the cost of assigning a decoy to a threat. For this, we first assume that the threat moves in a straight line towards the asset from the time when we detect it. And then this nominal location, this destination we want to send the decoy to, should satisfy the conditions for which we can actually do the spoofing with a high probability. So I mentioned before that we can only seduce the threat if the threat lies outside a certain range from the asset, the so-called burn-through range. So it's defined here. So the distance of the threat from the asset, the threat being the position of this threat being Z here and the position of the asset Y, needs to be larger than this range. And this range, in fact, is a function of the distance of the decoy to the threat and some electromagnetic parameters where antenna properties come into account. So we see this condition, we can only break the lock if the threat is sufficiently large away, but it also depends on how close this bound becomes harder if the decoy is far away from the threat. And actually we can, with the assumption that the threat is traveling in a straight line, we can pick a point on the line between the threat and the asset as the destination we want to send the decoy. And we can solve, this is a quadratic function of these distances. So we can actually find a closed form solution of which point on this line between the threat and the asset will remain valid for seducing the threat the longest. So there is this closed form solution. So this electromagnetic parameter squared divided by 4, this distance away from the asset will remain a good position where breakthrough conditions don't hold yet, so we can do the seduction for the longest time. And so if with this position we can compute the time it takes for the decoy to get to that position, and if the duration of the decoy getting there is longer than the time it takes for the threat to go there, then we know that this point is not valid. So this point, this position, this G, we say the nominal seduction location or target destination, is a valid target if the decoy is close enough. So we can do this for every threat, and then with this with the difference of this to this position to the initial decoy positions, we get weights, assignment weights for all decoy and threat pairs. We can then write this as a graph problem. So we consider a bipartite graph where we have a set of edges that represent the decoys, here shown in blue, and a set of edges that represent the threats. And the weights in this graph are the estimated time it takes to travel to those nominal seduction locations I talked about before. Now, in the bottleneck assignment problem, we want to find a matching. So a matching in this graph such that the largest weight in the matching is minimized. In this case here, this would be this edge here shown in red with weight 4. So agent or decoy 2 and threat 2 is a so-called bottleneck edge. But we see, in fact, there are several bottleneck edges. There's this edge and this edge. And there's actually several assignments that produce a bottleneck weight of 4. So the assignment shown here in dashed is a maximum cardinality matching. It is a valid assignment, and its highest weight is 4. So it's a bottleneck optimal assignment. But also the assignment showed in the dotted lines here, so this one, the same middle edge and this edge are also bottleneck optimal assignments. So we see this is not unique, and it also minimizing the bottleneck cost does not define the full assignment. The objective function, the bottleneck assignment problem, does not capture the values of the edges that are not the bottleneck itself. And so to extract properties of this graph, we look at how sensitive a particular assignment is to changes in the weights of the assignment graph. So changes or errors in the estimates of the weights, of the traveling time, or actually deviations in the positions of the agents. So for this, we define what we call a robustness margin, which is the difference of the bottleneck edge and the bottleneck edge obtained when we remove a bottleneck. So in this case, it's the difference between the graph when we solve the bottleneck assignment problem on the full graph. We get this red is a bottleneck. If we remove this edge and then solve the bottleneck or minimize the bottleneck, this orange edge here, 7, is a bottleneck for that graph, and the difference is what we call the robustness margin. And this robustness margin is interesting, or we will relate this later on to properties of or related to positions in the case of when these weights are proportional to distances. So we're interested in seeing how much can these weights change, because from this we can derive properties for navigating the agents. And so as I said before, the bottleneck assignment problem specifies, has some specifications for an optimizing assignment, but it doesn't specify the full assignment. So I tried to illustrate that before, but if we go through this, this is the same graph before. This is the full assignment graph. If we, from this analysis, say this is a bottleneck agent, so we will definitely assign agent 2 to task 2. But then we want to see what do we do with the other 2 remaining tasks that have to be distributed. So we perform what we're calling a sequential bottleneck assignment. So where the first step is the normal bottleneck assignment, and then we remove the agent and one tasks that we have assigned in that step. We then obtain this reduced graph and do the same thing here. We look at a bottleneck edge, which is shown here again in red. And as before, we not only look at the assignment or the edge, the bottleneck edge, but we also look at what the difference is of the best assignment to the second best assignment. So here in this case, the largest edge of the second best assignment is this edge shown in orange. So the robustness margin for the second iteration here is 2. So this orange edge minus the red edge. And then again, we remove this edge and we obtain a smaller problem. And then here we only have one task, but there's still 2 agents. And of these 2 agents, of course, we pick the lower weight edge, and the difference to the second best assignment is 6. So at every step of this sequence of assignment problems, we select an edge, we assign one task to an agent, and we also look at we also store or look at the difference of the best assignment to the second best assignment. So we say for every order, we have a bottleneck edge, so the kth order bottleneck edge, and also the kth order robustness margin. And then we've shown that that if the robustness margin is positive for all orders, then this sequence of bottleneck assignment problems is unique, which makes sense, and it is lexicographically minimal, the lexicographical minimum assignment. What that means is it's the assignment that has the smallest, largest weight. So that's the first criteria. If there's another assignment with the same smallest, largest weight, then its second largest weight is smaller, and so on. So there's no assignment that has a weight of low order that is lower than the lexicographically optimal assignment. So in some sense, we minimize the worst case. Given that that's minimized, we minimize the second worst agent task pairing. Given that's minimized, we keep going down the orders. So now, this can be used in navigating decoys or agents in general to destinations if we make certain assumptions. So if the assignment weights correspond to distances between target destinations and starting points, then we can relate all these distances to positions of the decoys amongst each other when they go there. So for this, we first assume that two agents, or 2 decoys in this case, have some finite extent, but we assume we know their diameter, and they do not collide if they are sufficiently far apart. So if they are further away, if their centroid positions are further away than the average of the diameters, then they do not collide at a certain time. So with this, we can say there's a safety distance. So we know the size of all the agents. We can say there's some safety distance that if the centroid positions of all the agents are further away than this safety distance, none of the agents collide. And we then assume, so we're doing this sequential bottleneck assignment I discussed in the last slide, and storing all these robustness margins at every step. We assume that the robustness margins are positive and that they are sufficiently large so that they correspond, so they, the distance that these weights correspond to are greater than the safety distance required for two agents not to collide. We can then construct local constraints for every decoy that is composed of two components. So we say that a decoy is bound by the range from its initial position by some bound that is increasing over time, and it is bound with the range from its destination. So here G, this G is its destination of the agent we're looking at, and PI0 is its initial position, and P is its current position, or this is any P in the set is the position constraint we're looking at. So if the position is close enough to initial position and to the destination, and if all agents do this, we have collision avoidance properties. So these two bounds, or this constraint set can be looked at as the intersection of two balls with some distance norm. So here we're looking at the infinity norm, but this will work for any distance metric. So we're looking at two balls, one centered around the destination of the agent, and one centered around where its origin, where it came from. And if the robustness margin is big enough, so these bounds are get bigger the more robustness we have. Mu here is the robustness from the robustness margin we introduced in the last slide. So the more robust the assignment is, the bigger this bound becomes, and the more these two balls intersect. And if the robustness margin is large enough, then these balls will intersect. And so then for every agent, we have such a position constraint. And so this bound increases with time. So we have some nominal velocity, so some scheduling variable between all the agents. We have this bound from the initial position that increases, and a bound from the destination that slowly decreases. And this increases up to a certain value, and then it saturates. And so for every value agent, there's a different saturation value, which is dependent on the robustness margin, and also there's it saturates at a lower bound as well. So this is for an agent that is assigned to a destination. For agents that are not assigned, so I said before, we assume there's at least as many decoys as threats, so there may be more agents than tasks. If there are more agents than tasks, then some tasks will not be assigned to go to any destination. And for them, we also construct a position bound, but it consists only of this first bound. So we only constrain the distance of an unassigned agent from its initial position. And so the result that we proved in the paper we just recently published was that decoys assigned to a destination will not collide with any other agent if all agents satisfy their local position constraints. So that gives us, in essence, local constraints for every agent. So we have safe sets for every agent, and these bounds are convex. And if all the agents satisfy these conditions locally, we decouple the motion planning of all the agents when they move together, and we can guarantee that collisions do not occur. I will illustrate this in the case study towards the end, but I now want to actually move to the actual motion control problem. I'll go through this a bit faster. I'm a bit slow. So for positioning the decoy, we have the objective of moving the decoy such that it can seduce the threat as soon as possible. And what we're optimizing is over some input. In this case, we're using a very simple model. So we're saying we are commanding reference velocities. And so we're looking at a time optimal problem where we're trying to minimize the positioning time. And so this is now for each decoy individually. So for decoy I assigned to threat J, we want to minimize the time steps required in the discretized model. We want to minimize the time steps required to the point where we satisfy conditions that we can start the seduction of the threat. And we have, so we said we minimize over the input sequence, over a sequence of inputs. So we have a finite prediction horizon, and we have a whole series of state constraints, and we're considering some disturbance in the model dynamics. So we're saying we're using a very simple model, but we'll have a robust formulation to compensate for model mismatch or uncertainties. So the first, we have input constraints and system state constraints that might arise from the modeling or from physics in general, or obstacle we want to avoid, or anything else. But then we also here isolate and give special attention to two particular constraints. So first of all, we want to decouple the motion planning of all the agents. And we do this with these local safe sets we've obtained from the task assignment in the previous step. And then here now we want to look at actually encoding the specification we have. So this will result in a state constraint. So as we said, we want to reach some place with the state being position and velocity, meaning we need to reach some place within the state space. And we also have requirements that the Doppler shift is not changed too much. So this is a constraint on the velocity. But we have these constraints are combined with each other in time. So we actually have temporal logic constraints, and we want to so we want to come up with state constraints that are derived from, or that correspond to the satisfaction of temporal logic specifications. And so for this, we use the language of temporal logic. So LTL, or linear temporal logic, is a way to formulate specifications in logic and time. And the LTL formula consists of a combination of atomic propositions that are combined with logic operators and temporal operators. So an atomic proposition is a statement that takes binary values, so it's either true or false. And in our case now, we're saying that we associate this true or false. We say there's a corresponding polyhedral set in the state space, where so the statement is true if the state lies within this polyhedral set, and it's false if the state does not lie in this set. So specification is satisfied at time k, so in a discrete time sequence now, we say this specification starting at the sequence of states starting at time point k and of length L satisfies the atomic proposition if it's the element or the first element of the sequence at that time is in this polyhedral set. And then we can go through and define the values of, or evaluate the values of LTL formula by combining sub formulas with the different operators. So the logic operators are pretty straightforward. So we say that a proposition is satisfied if the state at that the first element of the sequence lies in the polyhedral set. We say it's not satisfied if the opposite is true. And conditions are straightforward, and OR conditions as well. We need both to be satisfied. The temporal operators then combine logics in different time steps. So the next operator next of a formula is true if in the next time step at time k plus 1 the formula is true. And then more complicated are the operators until and release. I won't go through the exact detail here, but it's somewhat intuitive, but you always have to go through and check the exact definitions, as some of these operators seem very similar. But the until operator is something we will use in our specification, and it basically says that if you have one formula until the other one, it means that within your horizon you eventually have to satisfy the second formula, and until then satisfy the first one. And so with all these basic operations, we can define all the specifications that we typically deal with. But then there's macro operators that combine these. It simplifies things. So and in fact we will use them. So typical operators that are used are eventually, which is true until something happens, and always. Always is intuitive, that you always want something to be satisfied. That can be written as a combination of false and a release. And so for the task of positioning a decoy, the specification or the way we model the mission is as follows. We say we eventually want to be ready to seduce a threat J. So that is a combination of 3 atomic propositions. So the atomic propositions for statements for any time. So we say at any time we are interested if, or we want to say if decoy is in the tracking cone or not. Then we have the condition on the burn through range. The threat is in the burn through range or it isn't. And we have the Doppler shift condition. So if the Doppler shift is bounded, the threat cannot detect that it's being seduced, then that is also an atomic proposition that the Doppler shift is bounded. And we combine these 3 propositions for our mission. Specifically, we say eventually we are in the tracking cone and not in a burn through condition, and from then on always the Doppler shift is bounded. so this specification sums up the whole mission of the decoy, or the positioning mission of the decoy, in this language. So then we look at, for each of these atomic propositions, how do we encode them as these polyhedral sets. So the tracking cone is defined as a cone that has its apex at the position of the threat, and its orientation is towards the asset, and then there's a parameter of how much how wide the opening angle of this this cone is, the aperture is. And so this is a nonlinear set, but we then make an inner approximation with 5 half spaces. So I'll have an illustration of this later on. So we have this cone that is this quadratic or round object, and we approximate it with a set of a bunch of half spaces. We take an inner approximation so that if the atomic proposition is true, then we definitely have that the cone is in the decoy is in the cone. And then for the second proposition, which is that the burn through that the threat is in burn through. So this was originally formulated as a bound on the distance of the threat from the asset. So if the threat is too close to the asset, it is in burn through. I think I've got this in the wrong. This should be smaller then. So we have burn through if it is too close to the asset. But we make here, this can be reformulated as a condition on the decoy position. So we need the decoy to be close to the threat. So in other words, if it's too far away from the threat is in burn through. So we have this bound. So if this distance is, so a lower bound on the distance for the burn through to occur, and we take an outer approximation of this because we have a negation here. So in the end, we want to constrain the opposite so that we never have this condition. So that in this case, we take outer approximation so that if it is not satisfied, we constrain for what we want. And then the third proposition is the condition on the Doppler shift. So the Doppler shift of the decoy should not be too different from the Doppler shift that from the asset. So from the perspective of the threat, the difference of the decoy should not be too different from the asset. And the Doppler shift is a function of the velocity or the relative velocity of the decoy towards the threat. And so in essence, the Doppler shift condition corresponds to a constraint on the velocity. And from this, we construct a polyhedral bound on our state space, which is position and velocity. So we get another 2 half space constraints from this proposition. And so we have defined all our proposition and our specification, because of our propositions are associated with these polyhedral sets, we can write constraints that are linear in the state, and we introduce an auxiliary variable, which is mixed integer, so it has continuous valued variables and binary variables, and we can encode the constraint of satisfying the proposition, as a mixed integer constraint, but it's a linear mixed integer constraint. So these binaries, how do they come up? So for every half space, in every proposition, so we had 3, and every proposition had a different amount of half spaces defining those polyhedral sets, and every time step. So for every half space, in every atomic proposition, and every time step, we need to check on which if the state is in that half space or not. So we introduce a binary variable for each of these cases, and we use the big M method, where we can encode binary variables. So we can encode them that the binary is 1 if and only if the inequality holds, or we can just do one or the other. So in some cases, it might be beneficial to only encode one direction. So we want that the binary variable being 1 implies that the constraint is satisfied, or the opposite, or both. And then we introduce auxiliary variables for every operator we use in our specification. So for every and or the eventually operation we have, we introduce another auxiliary variable that will take binary values, but we can actually, it doesn't have to be a binary, we can just bound it between 1 and 0, and because everything is linear, the solution will take value in 1 or 0. So, but we have these auxiliary variables for every part of the formula. So for every LTL component, or every component of our specification. And if this variable is 1, it means that at a certain time, it means that the sequence of the state starting at that time satisfies that specification, or that part of the specification. And so with this, we can encode the constraint, which is given up here in the box, but we can also use this to construct the objective function in our optimization problem. So if we say we want the overall or formula, the overall goal specification to be satisfied at time 0, then we can minimize the time steps until the condition is first met. So we can use these auxiliary variables we've defined and to upper bound the number of time steps it takes to satisfy the condition the first time. This works. This is not a general approach. You can't always encode a meaningful objective function from these auxiliary variables, but in our case, because we have this eventually, we can use this to encode our objective function, and it relies on that we here only say that having this auxiliary variable being 1 implies that the specification is satisfied, and not the opposite. So the specification being satisfied at a particular time step does not mean that the auxiliary variable corresponding to it is necessarily 1. So with this, we can now formulate the time minimum problem we had for the motion control of the decoy as a mixed integer linear program. So we had the 3 types of state constraints. So just the satisfying the system constraints robustly. So we had disturbance for all disturbance. It can be encoded as a constraint. So for every row, so we have a set of constraints with many rows for all of these functions, and they need to be satisfied for all disturbance. So every row is we maximize of all rows, and for all disturbance, these inequalities have to hold, where these functions xi, lambda, and sigma are all linear in the state, sequence, input, and the disturbance. So for the input and state constraints, this is straightforward. If we're taking a linear model. For the collision avoidance, we have the position constraints I defined in the task assignment part. These were, when we're using the infinity norm or the one norm, these were linear constraints, so that's also straightforward. The tricky part is here, the specification constraints. So we want, on the previous slide, it was that the state, the specification is satisfied if there exists an auxiliary variable such this inequality is satisfied, but we need this for all the disturbances. So this results in a max min max, which is difficult. We can't really solve that. So if we switch the orders of the quantifiers here, so we say there exists an auxiliary variable such that for all disturbance the inequality is satisfied. Then we've made an inner approximation. So the value of our objective function might actually go up, but this is now in a shape where we can solve the problem. So we can include the minimization of the auxiliary variable. So we can include this in the optimization. We optimize over this, and then this is now in a form that can be solved easily using linear programming duality. We can solve this with off-the-shelf solvers. So we did this for an example, and I'll see I'm being very slow. I'm sorry. I'll speed up. So I just want to show some simulation results. So we're looking at a scenario where we have 10 decoys and 8 threats shown here. So the red dots are the threats, and we have the acid in the middle, and very small, you can hardly see it, the decoys. So the threats are detected at between 25 kilometers away, and moving towards the acids. The magenta areas here are the tracking cones. And if we zoom in, we see, so the colored dots are the decoys, and the black dots are the nominal seduction locations we had started off with. So with these locations and initial starting points, we can define assignment weights, so that are proportional to the distance of the positions to these locations. And we get these kind of, this is a table of all the weights for every agent and every task. And all I want to show you is here that the elements that are red in this table correspond to nominal seduction positions that cannot be reached before the threat goes here. So we see this is actually time critical, so we can't naively assign decoys to threats. So some combinations will not work in our, at least based on our first approximate analysis. But then here in green shows that we see the sequential bottleneck assignment. So we see we can find an assignment, and the largest cost is, or the bottleneck cost here is 65 seconds. So that's the largest estimated cost, or the largest time. And we do the sequential bottleneck assignment. So we go through, after finding the bottleneck cost, we go through and minimize all the other remaining assignments. And we see that the robustness margin for all of them, for all orders are positive. And so we have a lexicographically optimal assignment, and the smallest robustness margin corresponds to 200 meters if we relate it to the distances. which is bigger than the required distance we have between agents. So we assume that none of the decoys is larger than 2 meters. So we have some robustness or some margin in the position that is significantly greater than the size of the decoys. So here I want to illustrate for this scenario these time varying sets, these bounds that I was talking about in the assignment part. So at time 0 first, we start off, these colored boxes are where the agents are. There are 2 decoys that are not assigned. I'm showing them here. They're also constrained, but they're very light color. You can hardly see them. They're not so important. We're focusing on the decoys that are assigned to these threats, and which threat they're assigned to is illustrated with the dashed line. And so if we see over time, we can propagate or we can move the bound forward. And so for every decoy, if we look at this one, for instance, we have this cube or this box, which is the intersection of an infinity ball around the initial position of the decoy, and it's the destination of the decoy where it's assigned to. And so for every agent, we have these sets that are non-empty, and they move towards target. And then we do, that was just for the local safe sets. We implemented the motion control problem in YAML and Garobi on my laptop. And so here I'm showing that we're taking for the planning, we've got a very crude model and sampling time of 2 seconds. And we're looking at a prediction horizon of 32 steps, so about 60 seconds. And so again, we see the same scenario as before. We're going to focus on this decoy here, on decoy number 9, that is assigned to threat number 2. So just for them, I'm showing the box. We see here, so this decoy, we show the safe set and the threat. We have the tracking cone in cyan and our approximation of the tracking cone in green. So the approximation, the inner approximation is time varying over time. We'll see how this moves, and the decoy moves, and it has to stay within its safe set, which moves towards the nominal position. And we see actually at time step 18, the specification is predicted to be complete. And so this was an open loop simulation. So we computed at time 0 and applied the sequence over its whole horizon. So that was, there you can see the positions. We also here have one of the states is velocity. So we have here the velocity relative to the threat, which gives us the Doppler shift. And so remember, the requirement was that we have to reach a position eventually, and then from then on, the Doppler shift has to be bounded. And we reached this condition at time step 18, which corresponds to time of 36 seconds. So we see from at this point on, this constraint is active, and the Doppler shift is bounded from there on. And then we also tested or applied this in a more complex simulation where we have uncertainty that we don't incorporate into our model. So we also look at uncertainty of the threat in this simulation. And we re-optimize in every step. So we have a shrinking horizon. We see with the closed loop performance, with closed loop, so by re-optimizing and measuring the uncertainty in every step, we achieve a lower time of positioning a decoy across the board. And just here, I just want to show an image of what that looks like. So this is after 32 seconds.
Tony, can you wrap it up in 1 minute? Sorry.
Yep.
Yeah, you're over time.
So just this is a top view of the closed loop simulation. we see that the decoys position themselves and have started pulling the threats away from the asset, which is in the center here. So yeah, sorry, I was a bit slower than I expected. That's all I wanted to say. So in summary, we looked at methods to assign agents to tasks for navigation problems. And based on a robustness analysis of the assignment, we derived properties that can be used for to decouple the motion control problem. And we use temporal logic to formulate this motion control problem. What I didn't talk about here is distributed computation. So all of this, we didn't solve this in a distributed way, but all of this should be able to be distributed across the agents. So yeah, I'm going to finish with that. I don't know if we have time for any questions.
I'm going to stop the recording. Thanks, Tony. But anyone who wants to hang around and ask questions, just feel free to stay. Tony can probably hang around for some time as well.
Yeah.
Thanks, everyone, and see you next week for our next talk.